I'm going to give a demo of the example solution to the attacker challenge in the machine learning security evasion competition. The models to be attacked have been submitted by participants of the just completed Defender challenge. 2 of those models from the previous round have qualified to be included in the attacker challenge. In addition, we have hosted our own model trained on the Ember dataset that has basic capability to detect adversarial examples. The source code and weights for that model are provided on the competition GitHub site. However, the remaining models are complete black boxes to you, where you observe only the hard label outputs, a 0 or a 1, for inputs that you provide. The final leaderboard ranking will be established by the following rank ordered criteria: the number of model evasions, with 1 point for each of 3 models evaded times 50 malware samples, meaning a maximum score of 150. Remember, though, that each evasive variant must produce its original functionality in a sandbox in order to be awarded a point. That functionality is verified when you upload a zip file containing a package of evasive samples. It will not be verified when you merely query the machine learning models through the API. In the event of a tie, contestants will be ranked subsequently by the number of model queries through the API. Lastly, any third-way tiebreaker would be based on the timestamp of a final zip upload. More than likely, we won't even get to number 3 in the tie-breaking process, and so you should feel incentivized to continue competing even when you see a perfect score on the leaderboard, because you might achieve that same score but do it more efficiently. As a contestant, you can choose any strategy you like. To demonstrate one possible strategy, we've released example code on the competition site. The code uses discrete optimization over file modifications using hyperopt, which ironically is often used to tune machine learning models. You can learn more about the details of the algorithm from the code and from the documentation. However, the broader strategy might be of general interest no matter your approach. It consists of employing an algorithm in part A to get the bulk of the malware to be evasive while remaining functional, followed by any manual cleanup needed in a part B to fix any few remaining samples. In the example code, the algorithm in part A tries to be parsimonious in its use of the API by first conducting an offline attack against the Defender Ember model, for which we have code and weights. Then we'll use the candidate samples from that offline attack in an online attack against the hosted models. The hope is that many of the samples that were discovered in the offline attack will cross-evade the hosted models without having used any queries against the API. So when you run this demo code, please do so using a Linux VM. This will write malware to disk. To begin, we initialize the attack by analyzing a collection of benign files. The init subcommand extracts elements of the benign files that will be injected later into the malware. To launch our offline attack, we run a local copy of the Ember model in the upper window. Then in a separate lower window, we'll use the run subcommand, passing in the malware samples you downloaded after registering on the website. The tool will write successful evasion attempts to a folder of our choice, pass1/success, and failed attempts to a different folder, pass1/failure. Also included in each directory are a history of modifications that would allow us to resume any failed optimization attempts. So to demonstrate that, in a second round, in a second pass of our offline attack, we'll begin by using the pass1 failures as seeds and again iterate on the optimization, storing again the successes and failures in a pass2 folder of our choice. Having now collected candidates that evade the Ember model, we can collect them and use those as seeds for an online attack, and now have those queries count against us on the leaderboard for our API usage. The online attack is simply enabled using the -- online flag with the tool. After several iterations, we can now create a zip file containing our evasive variants, and those would be checked first in a Windows 10 sandbox, then uploaded to the website for ranking in the leaderboard. Since there is a chance that the file modifications have broken some of the files, you should run those samples in a Windows 10 sandbox before uploading to the competition website. In fact, as a final note, since the hosted models might actually be learning or changing state based on the queries that you provide them, and those of others contestants also, there is a possibility that an evasive variant that you discover during the process may no longer evade a model by the time you upload your zip file. So what counts is at the time of zip file upload, those evasions can be locked in and counted on the leaderboard. The competition began on Thursday and will conclude in a little over 6 weeks. Please do visit the website for more information and to register for the challenge. Remember that in order to receive one of the 2 prizes, you must both win and share publicly in some published format your solution, like on a blog or a white paper. Finally, I would like to thank our competition sponsors and partners for making this competition a reality. Good luck.